Over the past few million years, whales have been evolving toward greater and greater sizes. Today's whales are, on average, much larger than their ancestors. Dinosaurs ruled the planet for 165 million years, and the largest land dinosaur we know of, Argentinosaurus, weighed about 90 tons. Impressive, yes, but the blue whale doubles that. In fact, the tongue of a blue whale alone weighs as much as a full-grown elephant. Its heart is the size of a small car, pumping 10 tons of blood through its body. Just one breath from its lungs can fill nearly 2,000 balloons. So, here's the mystery. Why are the oceans producing animals even larger than the mightiest land giants? And even more curious, why does it seem like whales are still pushing the limits of size? Evolution usually strikes a balance. Bigger isn't always better. Being massive means needing more food, more energy, and more time to grow. For most species, there's a natural sweet spot where the advantages of size level out against the costs. But whales appear to have broken this rule. They've kept stretching the boundaries. This raises some fascinating questions. What changed in Earth's history that allowed these ocean mammals to become so huge? Why did gigantism become their winning strategy? Is there an upper limit? Or could whales get even bigger in the future? Evolution is usually about survival, not size. So what made size the winning ticket for whales? When we think of whales today, we imagine immense bodies gliding effortlessly through the water. But if you traveled back 50 million years, you wouldn't see giants. You'd see something that looked more like a wolf with webbed feet. Meet Pachycetus, the very first whale we know of. About the size of a medium dog, Pachycetus lived near rivers and coastal areas in what is now Pakistan. At first glance, it didn't look much like a whale at all. It had legs, fur, and teeth designed for crunching fish. But if you look closer, one detail gave away its future: the structure of its ears. They were already adapted for hearing underwater. Evolution had begun writing the first chapter of the whale's oceanic destiny, because the ocean offered something land could never give. After Pachycetus came Ambulocetus, whose name literally means the walking whale. Imagine a creature as long as a crocodile, with legs strong enough to walk on land, but also powerful enough to paddle through rivers and coastal lagoons. Ambulocetus was like a crocodile-mammal hybrid, an amphibious predator that could ambush prey both on land and in water. It was larger than Pachycetus, but still nowhere near the titans of today. Then came Basilosaurus, about 40 million years ago. Don't be fooled by the name. It's not a dinosaur, but a fully aquatic whale. And it was the first to truly become enormous by ancient standards. Stretching up to 20 meters long, Basilosaurus looked like a sea serpent with a long, eel-like body. Unlike modern whales, it had tiny back legs, useless for walking, but still a fossil reminder of its land-dwelling ancestors. Basilosaurus was a fearsome predator, swallowing sharks and fish whole. Still, Basilosaurus wasn't yet a giant in the sense of today's blue whales. It was long, but relatively slender. The true explosion of size hadn't started yet. So, what happened next? For millions of years, whales experimented with different lifestyles. Some evolved into toothed hunters. Others developed baleen plates, giant comb-like filters in their mouths, allowing them to gulp seawater and sieve out tiny shrimp-like creatures called krill. This shift, from hunting individual prey to filter feeding on billions of tiny organisms, was a game changer. But at this point in time, whales were still only moderately large. The real boost, the moment when whales began to truly supersize, came much later, during a period of dramatic change in Earth's climate. Because as it turns out, whales didn't just grow because they could. They grew because the oceans themselves changed, providing a superabundance of food. That story, of oceans turning into an all-you-can-eat buffet, is where gigantism really begins. For tens of millions of years, whales swam the seas as respectable predators and filter feeders. Some were long and snake-like, like Basilosaurus. Others evolved into early versions of toothed whales and baleen whales. They were large, yes, but not yet record-breaking giants. Then, about 3 million years ago, Earth's climate shifted dramatically. The ice ages arrived. Glaciers expanded, covering vast parts of the northern hemisphere. And with this frozen upheaval came a hidden gift to the oceans: nutrient-rich waters. As glaciers grew and melted in cycles, they changed the way oceans circulated. Cold water from the poles began mixing with warmer tropical water, stirring up nutrients from the deep sea and spreading them across vast regions. These nutrients, nitrogen, phosphorus, iron, are like fertilizer for the ocean. Suddenly, vast blooms of plankton appeared, covering the seas like invisible meadows. And where there is plankton, there is krill. These tiny shrimp-like creatures might not look impressive, but together they form one of the largest biomasses on Earth. Trillions of krill swarm in giant clouds. They are the foundation of the marine food chain, the rice of the sea. Now, imagine being a whale during this period. You've got an ocean bursting with food, stretching for thousands of miles. Whales with larger bodies, larger mouths, and larger energy reserves could scoop up more krill in a single gulp. They could travel farther to follow these food blooms across seasons. They could dive deeper, store more oxygen, and feed more efficiently than their smaller cousins. This was the evolutionary jackpot. Whales that could eat more survived better. Whales that survived better passed on their genes. And slowly, generation by generation, the whales that thrived were the ones that got bigger. Instead of chasing one fish at a time, they evolved a method called lunge feeding. Picture this. A whale opens its mouth wide, wider than a school bus, and charges into a swarm of krill. Its throat pouch balloons like a parachute, taking in 70 tons of seawater in one gulp. Then it closes its mouth, squeezes the water out through its baleen plates, and leaves behind a wriggling mouthful of pure krill protein. One gulp can fuel a whale with millions of calories. But to make this feeding style efficient, size mattered. A small whale could lunge, sure, but the payoff wouldn't be worth the energy. A giant whale, however, could make every gulp count. This is when whales truly began their rise to supergiant status. The ice ages didn't just challenge life on land, they transformed the oceans into a banquet hall for the biggest eaters. And whales, already evolving toward filter feeding, seized the opportunity. It's no coincidence that the largest whales we know today, the blue whale, the fin whale, the sei whale, all belong to the baleen family. They are direct beneficiaries of this oceanic buffet, scaling up to sizes no land animal could ever match. Because, remember, on land, gravity limits size. An animal the size of a blue whale would collapse under its own weight. But in water, the ocean itself helps carry the load. Nutrient-rich seas, efficient filter feeding, and the buoyancy of water. The result? The rise of the ocean giants. But size wasn't just about feasting. Evolution had other reasons for making whales enormous. Because in the dangerous oceans of the past, being big didn't just help you eat more, it helped you stay alive. And that's where our story heads next. When we think of whales today, it's hard to imagine them as anything but the undisputed rulers of the seas. But not so long ago, in evolutionary terms, the oceans were far more dangerous. To survive here, whales needed more than just food, they needed protection. And in the animal kingdom, one of the best defenses is sheer size. Let's rewind about 20 million years. Whales were already well established, but the oceans also had another apex predator, Megalodon. This gigantic shark, stretching up to 18 meters long, was the terror of the seas. With jaws big enough to swallow a human whole, smaller whales were easy targets. But larger whales, they were harder to attack, harder to overpower, and often too big for even Megalodon to handle. Over millions of years, whales that could grow bigger stood a better chance of passing their genes on. But predators weren't the only pressure. The open ocean is a harsh, unpredictable place. Food isn't evenly spread. It comes in patches, and sometimes you have to travel thousands of miles to find it. A small animal can only carry so much energy. A large whale with massive fat reserves can cross entire oceans, fasting for weeks during migrations, and still survive. Their size became their passport to roam Earth's seas. And then there's the diving advantage. A larger body can store more oxygen, allowing whales to dive deeper and stay underwater longer. Today, sperm whales can dive over 2,000 meters and hold their breath for more than an hour in pursuit of giant squid. Their massive size makes that possible. Smaller lungs and smaller oxygen reserves simply wouldn't be enough. Size also plays a role in social behavior. For baleen whales, migration often means traveling from polar feeding grounds to tropical breeding grounds, journeys of thousands of kilometers. Only enormous animals with colossal energy stores can make these round trips every year. In other words, gigantism became a multi-tool for survival. Too big for most predators. Big enough to store energy for long voyages. Big enough to dive deep for food. Big enough to thrive in oceans that reward efficiency on a grand scale. And then, something remarkable happened. Around 3 million years ago, just as the ice ages were reshaping the oceans, Megalodon went extinct. Scientists still debate exactly why. Cooling oceans, loss of prey, competition with emerging killer whales. Whatever the cause, its disappearance removed a major check on whale evolution. Without the shadow of Megalodon, whales were free to become even larger without fear of being hunted. It was as if nature had finally said, "Go ahead, grow as large as you can." And so they did. Whales pushed size to levels never seen before in Earth's history. Earth has seen giants before, towering dinosaurs like Argentinosaurus, monstrous reptiles of the seas like Shonosaurus, and colossal land mammals like Paraceratherium. But none of them come close to the blue whale's scale. The blue whale doubles the size of most of the largest dinosaurs. Its daily diet? Around 4 tons of krill. That's roughly 40 million individual shrimp-like creatures every single day. Imagine eating 70,000 hamburgers daily just to stay alive. That's the whale's equivalent. And yet, despite this immense bulk, the blue whale is a master of elegance. Underwater, its body glides almost silently, powered by muscles so strong they can propel this living mountain at speeds of 25 miles per hour in bursts. To watch a blue whale swim is like seeing a skyscraper suddenly come to life and move with grace. Every part of its biology is designed around its massive size. This raises a profound scientific question. How big can a whale actually get? It feels like whales could just keep getting bigger forever. But nature doesn't hand out infinite growth. Every giant hits a wall. Let's start with the most basic problem: energy. A blue whale eats up to 4 tons of krill a day. That's about 1.5 million calories. To put that into perspective, it's the same as what 70,000 humans eat in a single day, all packed into one animal's diet. If a whale were to grow much larger, its daily calorie demand would skyrocket, and the math would stop working. Then there's oxygen. Larger bodies need more oxygen, but there's a catch. Breathing efficiency doesn't scale up as fast as body size. Blue whales have evolved incredible lungs that can exchange up to 90% of the air in a single breath, compared to humans, who manage only about 15%. But even that has a limit. At some point, no matter how efficient you are, a body too big simply can't fuel itself with oxygen fast enough. Next comes the mechanics of movement. To feed, blue whales perform high-speed lunges, engulfing masses of krill-filled water. But physics gets in the way here. As whales grow larger, the drag from water increases disproportionately. The energy cost of lunging rises faster than the calories they gain. Studies suggest this is one of the biggest breaks on whale size. And then there's the climate factor. The very reason whales became giants, the nutrient-rich oceans of the ice ages, is now under threat. Warming seas, changing currents, and human-driven overfishing are shrinking krill populations in many regions. Without enough prey, being enormous isn't just inefficient, it's dangerous. A body that requires 4 tons of food a day can't afford scarcity. For whales, climate change may not just cap their growth, it may even pressure them back towards smaller sizes in the distant future. So the question isn't just, how big can whales get? It might be, have they already reached the maximum size evolution allows? All evidence suggests they have. The blue whale is very likely the peak of biological gigantism, the largest size evolution can realistically support in Earth's oceans. They're not just record breakers, they're the upper boundary, the final chapter in size itself. Whales have stretched biology, physics, and the limits of Earth's food web to reach this point. They are quite literally as big as life can get. But while science suggests whales can't grow much bigger, their future size depends on something else, us. Because our actions are reshaping the oceans at a speed evolution can't keep up with. And that brings us to the final part of the story, the uncertain future of these ocean giants. On one hand, whales may already be at their peak. The blue whale is the ultimate balance point, the largest possible animal that can still find enough food, breathe enough oxygen, and move efficiently through the water. From a scientific standpoint, we may be living in the golden age of whale gigantism, witnessing the very maximum size life can achieve on this planet. But evolution is never static. It bends and twists with the environment. Millions of years from now, if oceans change again, if food becomes even more concentrated, or if new feeding strategies evolve, perhaps whales could push size just a little further. Or the opposite could happen. If climate change and human activity continue to deplete krill and disrupt ecosystems, the giants of today may find themselves in trouble. For an animal that needs 4 tons of food every single day, even a small decline in prey is catastrophic. In this scenario, natural selection could favor smaller whales, animals that need less food, travel shorter distances, and adapt more easily to a patchier ocean. Gigantism could slowly reverse.